I'm Anil Kumar. Welcome to my series on trigonometry. In this video, we'll discuss Introduction to Trigonometric Identities. We'll begin with understanding of equations, what are identities, what are trigonometric identities, and how, from given equation, we can figure out whether it is an identity or not. We might use counterexample for that. We'll take some basic identities and prove them, and then we'll understand strategies to prove identities. So let's begin with the concept of equation itself. An equation is a mathematical representation of statement when two expressions are equal. Here are examples for you. 2x minus 1 equals to 5 is an equation. X squared minus 8x equals to 7 is an equation. X plus y equals to 0 is an equation. And similarly, x squared equals to minus 1 is an equation. So what you really see in any equation is one sign which is equal to sign. So equation always will have an equal to sign, will have an expression on this side and another expression on the other side. So in mathematics, we're calling them mathematical expressions. And something in between will always be equal to sign. And that is equation, right? So we have an equal to sign. So this becomes an equation for us in general. Correct. Now here, what you notice is that the first equation which we have given, 2x minus 1 equals to 5, is actually true for only one value. And that could be figured out by solving the equation. So we could do something like this and say that x is equal to 6 divided by 2, which is 3. So this equation is true for x equals to 3. And that is the only value for which the equation is true. The other equation, let's try that to solve, is x squared minus 8x plus 7 equals to 0. You could factor this and write this as x minus 7 is 7 times 1, both negative, right? So we could write like this, factor. And then this equation is true for two values, x equals to 7 and x equals to 1. So we have in the first case one solution, and in the second case it is true for two values, which is 7 and 1. If I take the third equation, which is x plus y equals to 0, it is true for many values. So in general, from here we could write y equals to minus x. So for many combinations, it is true. For example, we could take a value as 0, 0, 1, minus 1, and so on. So we have infinite solutions. Is that clear to you? How about the last equation, which is x squared equals to minus 1? So let me write down here x squared equals to minus 1. So this is never true. Since the square of a number is always a positive number. So what you notice here is that equation may be true for some values, right? It may not be true for any value. So when we're talking about real numbers. So we say in the domain of real numbers, equations can have one solution, more than one, or even no solution. Still, it will be treated as an equation since it has the basic form, which is there are two expressions, and we always will mention the expression on the left side as left hand side expression and the other one as the right hand side expressions. So the equation has two expressions with equal to sign in between. That becomes the basics. Now let's see out of these equations which ones could be treated as identities. Here I've written the definition of identities. If the equation is true for every value of the variables for which both expressions are defined, then it is an identity. Otherwise, it is a conditional equation. Now, once again, getting back to a few more terms, technical terms, variables. So these lowercase alphabets which are used are termed as variables as they could have any value. Now, both expressions here means the left side and the right side. That is what we mean by saying both expressions, right? So, if the equation is true for all the values of the variable in their domain, we say, in that case it becomes an identity. For example, the very first one is 3p plus 5p. So if I add them, I get 8p. Now this is my left hand side expression. And on the right hand side, what do I have? On the right hand side, I already have 8p. So what I have shown here is that left hand side is equal to right hand side. Is that clear to you? Now that is true for all p, right? So technically we say where p belongs to real numbers, but let me keep it simple, true for all p. The next one here is x squared minus y squared equals to 0. Well, this is true only when x squared equals to y squared. However, if I change this to x squared minus y squared equals to x plus y times x minus y, then it is true for all values. So as you can see here, we have an expression on left side and an expression on the right side. This one is an equation, and the first one is an identity. Identity is true for all values. Here, x squared minus y squared is equals to 0 is not true for all values. It might have many solutions, right? But if I change it to x squared minus y squared equals to x plus y times x minus y, then it is true for all values. And I can show it by starting with the right hand side this time. Right hand side will be x plus y times x minus y. So if I expand and simplify using the distributive properties, that is, multiplying with x first, we get x squared, then x minus y is xy, then we get plus xy and minus y squared, which reduces to or simplifies to x squared minus y squared, which is same as the left hand side. So in this case, we have shown that right hand side is equal to left hand side, and that is true for all values of x and y. So that becomes an identity. You get the idea. So in general, we can say that if an equation is true for every value of variables for which both expressions are defined, then it's an identity. Otherwise, it is a conditional equation. So now I hope you understand why we changed equation into two things. So we are calling equation as an identity when it is true for all the values, and a conditional equation when it is not true for all the values, sometimes true for some values. That's the major difference between the two. The last one here is a very good example where we do have a restriction. Now, the last equation, x squared minus 1 divided by x plus 1 is equals to x minus 1, only when x is not equal to minus 1. This is not valid for x equals to minus 1, since that will make the denominator 0 and you cannot divide by 0. Correct? So, apart from this particular value, it is true for all the values. And that brings us to a very important part of this definition, which says if the equation is true for every value of the variables, so in this particular case, the variable x cannot have the value of minus 1. So we have restrictions. Now, if you have an equation with restriction, and if it is true for all values, it is still treated as an identity. So this still is an identity. Correct? So in this particular example, we have taken 3 in which all 3 are equations. However, first and the last one are identities. In the first one, we have no restrictions. In the last one, which is x squared minus 1 over x plus 1 equals to x minus 1, we have a restriction. X cannot be equal to minus 1, but it is true for all other values. The expression x squared minus 1 over x plus 1 has the same restriction, and therefore that value will be excluded from checking, and we say this is an identity. Perfect. Now let's move on and understand what is trigonometric identity. Well, in the previous examples, when we are talking about identities, we used the algebraic terms. Now, when we are saying trigonometric identities, then we do have an equation on the left side. We should write expression equal to another expression. Now, this expression will term as left-hand side expression and right-hand side expression with the equal to sign in between. Now, if we have within these expressions any trigonometric ratio, in expression, it could be anywhere on the left side or on the right side. So if we have any trigonometric ratio in expression, this will be treated as a trigonometric equation. Correct? Just as we were talking about algebraic equation in general, right? So if we have a trigonometric ratio in an expression, above expression, in that case we'll call it as a trigonometric equation. And if that equation is an identity, we'll call this as a trigonometric identity. Correct? Now in this video, we'll look into these different kinds of trigonometric identities: quotient identity, reciprocal identity, Pythagorean identity, even an odd function identity, co-function identity, and related acute angle identity. I'll also provide proof of these identities in this video. But before getting there, let's talk about another term which is very important to understand. It is counterexample. Now, let us try to understand the concept of counterexamples. It is a very important concept to show that the given equation is not an identity. So if you provide one example showing that left side is not equal to right side, in that case, it is sufficient to say that the given equation is not an identity, right? So what we are looking into is counterexamples. The question here is, are the following identities? We need to justify our answer. We have three equations here. The first one is x square root equals to x. Is it an identity? The second one is sine a plus b equals to sine a plus cos b. Is it an identity? And the third one here is sine square theta plus cos square theta equals to 1. Is it an identity? So the first one seems to be an identity. We have x squared square root equals to x. Now if you do most of the values, you will get the right result. However, if I say that x equals to minus 1, for example, in that case, minus 1 square root is what? That is equal to square root of 1, and this is equal to 1. So you can see that 1 is not equal to minus 1. So with one value of x equals to a negative 1, we have shown that the left hand side is not equal to right hand side. Is that clear? And therefore, from here we can say that square root of x squared equals to x is not an identity. Is that clear to you? Correct. So we have an example and we call this as a counter example. So I hope you have understood the concept. To prove an identity, we are trying to prove that left side is equal to right side. In this particular case, we took a specific example, a value of x as minus 1. When I substitute minus 1 on the left hand side, I get plus 1. And now, plus 1 is not equal to minus 1. And therefore, this equation is not true for all the values of x. And so, it is not an identity. Is that clear to you? So that is the concept of counterexamples. So I'd like you to use this concept of counterexample to show whether B is an identity or C is an identity, or they are not identities. Perfect. So I'll leave that exercise for you to show that whether it is an identity or not. So provide a counterexample to show that this is not an identity. So you can take a value of A, for example, 30 degrees, and the value of B as 60 degrees, and work it out. You could also take a value of A as 0 degrees and B also as 0 degrees and work it out. Correct? So sometimes it may work out to be correct, but not always. So if you get left hand side is not equal to right hand side, then that becomes a counterexample. Perfect. And then you can say whether it is an identity or not. So if you get a success in counterexample, it is not an identity. Correct? So I'd like you to try it out and write your answer in the comments. Let's move on and now prove the trigonometric identities. We'll begin with the concept of proving trigonometric identities. I'll actually take coordinate plane, and in a coordinate plane we had been representing a point with, let's say we have a point here P whose coordinates are x and y. Correct? So in our coordinate plane xy, we have a point P which is generally represented by xy. In that case, If I drop a perpendicular, and let's say this angle is theta for us, and let's say this is r, the distance from O to P, where r will be equal to square root of x square plus y square, correct? So r is going to be positive, and its value will be x square plus y square square root. Now in this particular triangle, when I drop the perpendicular, I get Q as my point on the x-axis. So let me redraw this particular triangle here. Let's say this is our triangle where the points being considered are OPQ. The angle is theta for us. This is the right angle triangle. O to Q is of length x, P to Q is of length y, and O to P is r, where r is equal to square root of x square plus y square. Clear? So what I've done here is I've just shown this triangle here. Now, let us try to understand how this particular triangle represents trigonometric ratios. So from here, we can say what is sine theta equals to. Sine theta is ratio of opposite side to hypotenuse. So sine theta can be written as y over r. What is cos theta equals to? Cos theta is ratio of adjacent side to hypotenuse. So cos theta can be written as x over r. As far as tan theta is concerned, it is the ratio of opposite side to adjacent side. So tan theta can be written as y over x. Now to prove the identities, we are going to use a point on the coordinate plane and sine theta as y over r, cos theta as x over r, and tan theta as y over x. Let's begin with the quotient identity. So when I say quotient identity, then it means the quotient identity is tan theta is equal to sine theta over cos theta. Now this is one of the most important identities. It's called the quotient identity. Getting back to the position itself, we had considered a point P whose coordinates were x and y, correct? So now, if I begin with the right-hand side is more complicated. So we could write, in this case, we know what is sine theta. Sine theta is basically equal to y over r. Correct? This is r, that is y, and this is x. Correct? For the angle theta, as we saw. And what is cos theta? Cos theta is x over r. What is tan theta? Tan theta is y over x. Correct? Now, in this expression on the right hand side, we have sine theta over cos theta. So sine theta is y over r, cos theta is x over r, which you could write as y over r times r over x. And so r and r cancel. What you get is y over x. Y over x is what? Y over x is tan theta, which is the left hand side. Do you see that? Correct? So have a good look at it. R and R cancel in this ratio of y over x over r. And what we get is y over x, which is tan theta. So here we have shown that the right hand side is equal to left hand side. And that is true for all theta. And therefore, it's an identity, and we call this as quotient identity. Is that clear to you? So that is a way to prove identities, some basic identities. We'll continue with this and prove all our basic identities, since to prove more complicated identities, we are going to take them as our base. Now let's talk about reciprocal identities. We have three reciprocal identities. One is cosecant theta is equal to 1 over sine theta. Then we have secant theta as reciprocal of cos theta, and cotangent theta as reciprocal of tan theta. Now these are also easy to prove. We can actually begin with right hand side. For example, we have 1 over sine theta. That could be written as 1 over. Sine theta is y over r, which you could write as r over y, and r over y is cosecant theta. Is that clear to you? So we have shown that the right hand side is equal to left hand side, and so we have proven the identity. The next one, let's do it here itself. 1 over cos theta is 1 over x over r, which is r over x, and that is secant theta. And the last one here is 1 over tan theta, which is 1 over y over x, that is the tan theta value, and this is x over y, reciprocal, and that becomes cotangent theta. So we have shown all the three in no time. Do you see that part? So these are called the reciprocal identities, and that is how you could prove it. Now let's take the Pythagorean identity. Now the Pythagorean identities could be written, there are three of them. One is sine square theta plus cos square theta equals to 1. The other one is 1 plus tan square theta equals to secant square theta, and the third one is 1 plus cot square theta is cosecant square theta. So these are the three identities which we need to prove. We'll begin with the very first one, and we can actually prove the later ones from the first one itself. Now the first one here is, let's begin with the left hand side in this case, since that is more complicated. So we could write left hand side as, let's do it the other way. So let me again sketch the um, triangle for us. It becomes simpler. So we have a point xy. So this is y for us, this is x, that is theta, this is r for us in a right triangle. So in a right triangle, we notice that x square plus y square is equal to r square, correct? That is Pythagorean theorem. Perfect. Now, see what happens when I divide by r square. So we have x square plus y square equals to r square. And if I divide all of them by r square, then we get x over r square, x over r, which is cos. Do you see that? So we get cos square theta plus sine square theta equals to r square over r square is 1. So we have shown the first identity. So simply by using the Pythagorean theorem, which is x square plus y square equals to r square, and dividing each term by r square, we got our identity, which is sine square plus cos square theta equals to 1. Now we could do the other ones also in the similar fashion. To show you the strategy, here it is. So let's again begin with this combination of x square plus y square equals to r square. Now let me divide by the term x square, all the three. So we get 1 plus y over x is tan. So we get tan square theta equals to r over x, which is secant square theta. So we have shown the second one. Now, if I divide by y square, then what do I get? So we have x square plus y square equals to r square. Let me divide by y square this time. So we get x over y, which is cotangent. So that is cot square theta plus 1 equals to r over y, reciprocal of sine, which is cosecant. So we get the third one. You get the idea. So that is how we could actually prove all the three identities. And since we use Pythagorean theorem, and it's very similar to that, we call them as Pythagorean identities. Perfect. So sine square theta plus cos square theta is equal to 1. 1 plus tan square theta is secant square theta, and 1 plus cot square theta is cosecant square theta. These three are very important identities, and we'll be using them so many times to prove identities. Perfect. I hope the proof is clear. Now, we could have shown this in other ways also, but for now, I think that works. Let's move on and look into other kind of identities. This is called even and odd function identity. Now here, what I'm trying to say is that if I have sine theta, then I could also, let me do even function. Let's try to understand what is an even function and what is an odd function to begin with. Now, even function is what? Even function is that if I take x as a minus value and if I get the same as f of x, then it is even. But if I replace x with minus x and if I get negative of the value, then it becomes an odd function. So that is the basic definition of even and odd. And now let's apply that to the trigonometric functions to show what we're trying to figure out. So to begin with, let us see what is sine of minus theta equals to. Let's go back to the quadrants. And in our quadrants, we learn that all are positive in quadrant 1, sine is positive in quadrant 2, tan is positive in quadrant 3, and cosine in quadrant 4. So when I say sine of minus theta, so sine theta is this one, right? Minus theta will mean we're talking about the point in quadrant 4. So as soon as I do sine of minus theta, then the point which was here, pxy, now is reflected and we get this point as x of minus y. Do you see that? So sine of minus theta in this particular case, the radius being the same, the hypotenuse being the same, could be written as minus y over r. And this is equal to minus of sine theta. And that is odd function. So we call this as our odd identity. You get the idea, right? Let me take up cos. So if I say cos of minus theta, it is equal to, here cos is still x over r. So it is x over r, which is same as cos theta. Now since cos of minus theta is cos theta and it is same, we're saying that f of minus x is f of x and they are even, right? So this is called even function. Is that clear to you? Now, can you tell me what happens to tan? So if I am looking into tan of minus theta, in this case, tan of minus theta will be minus y over x, that is this point, correct? Which is negative of y over x, which is negative of tan theta. So we get our three identities here. Let me summarize these three, write them here as sine of minus theta is equals to minus sine theta. Cos of minus theta is cos theta, and tan of minus theta is minus tan theta. Is that clear to you? So these are additional three identities. which are referred to as even-odd function identity. Now we have another type of identity which is called co-function identity. The concept of co-function identity is something like this. Let's look into our right triangle once again. In a right triangle, if one angle is theta, then what is the other angle? If this angle is theta, then what is the other angle? Well, the other angle has to be 90 degrees minus theta. Correct? Since it's a right angle triangle. Now, compare the two values. What is sine theta and what is cos of, let's say, 90 minus theta? Let's say this is y over us, this is x. Okay. In that case, and let's say this is r, the hypotenuse. In that case, sine theta is basically equal to the opposite side y over r. And now, what is cos 90 minus theta? For cosine, we have to look for adjacent side, right? It is also equals to y over r. So what you notice here is that sine theta is equals to cos of 90 degrees minus theta. So sine becomes cos when we're talking about 90 minus theta because we're looking from the other side of the right triangle. So opposite becomes adjacent, adjacent becomes opposite side. So that brings us to three important identities once again here, which we could normally write as sine of 90 minus theta equals to cos theta. They're all in degrees. Cos of 90 minus theta is equals to sine theta, and tan of 90 minus theta is what? Cotangent theta. Let's try to prove it. So in this particular case, let's try to prove tan theta now. So if I'm looking for tan of 90 minus theta, so you're looking from this side, right? This is 90 minus theta. So it is x over y. And what is cot theta? Cot theta is also x over y. So when you look from here, x over y, correct? So you see both of them are equal. So that is how you get these identities. These are called co-function identities. I like you to make a note of all these identities so that you have a big list of identities to begin with. The next one here is related acute angle identity. While solving equations, we did refer to related acute angles. Here is a quick review. Always, acute angle is within 0 to 90 degrees. So let's say acute angle. We normally put as alpha. So we know alpha is between 0 and 90 degrees. So somewhere in this quadrant, right? So this is your 0 degrees and that is 90 degrees. Now in this particular quadrant, all are positive. All means all trigonometric ratios. So all trigonometric ratios are positive for alpha, correct? Because alpha is between 0 to 90 degrees. Now, for any angle, we could have up to 360, right? Or its multiples. For any angle, we will see how the value is changing with different positions. So now, let's try to see the situation here in a bigger scale. So we'll talk about a triangle with an angle theta in quadrant 1. Now what happens in quadrant 2, 3, and 4? So if I have a triangle similar to this in quadrant 2 with the same angle theta as an acute angle. So we are talking about the acute angle theta. Let me name this as alpha to make it much more clear. Let's say this angle is alpha, the acute angle, so that we could use theta as a principal angle, correct? Now, in these two triangles, what you really notice is that the point P is xy here, and when you reflect it, then the point becomes minus of x and y, the distance of hypotenuse being constant. Now, in this particular case, you will notice that sine value is positive, and the angle here will be sine 180 minus theta. Correct? Let me write alpha, the related acute angle. Since the sine value is positive, we could write this as sine alpha. However, cosine is negative, so cos of 180 minus alpha will be minus of cos alpha, and tan of 180 minus alpha will be minus of tan alpha. Since we also know that in quadrant 1 all are positive, in quadrant 2 only sine is positive, tan is positive in quadrant 3, and cosine is positive in quadrant 4. So from this situation and the points, you could easily figure out that sine of 180 minus theta will be sine theta, but cos and tan of 180 minus theta becomes negative of their acute angle alpha. You get the idea, right? So that's the whole idea. The angle here, which we are showing, is 180 minus alpha. Now you could also show that if I'm working in the other quadrant, which is quadrant 3, in this quadrant, the angle will be what? Tan is positive. So tan of 180 plus alpha will be equal to tan alpha. Perfect. Because both the points will be negative. I mean, coordinate values will be negative. When you find the ratio, it will be positive. However, for sine and cosine, they will be negative. So we have sine of 180 minus alpha as minus sine alpha, and cos of 180 minus alpha as minus cos alpha. So these are your related acute angle identities. Correct. So with this, we have understood many identities. We learned into even and odd, which could be also treated as the angle in the fourth quadrant. Correct. So even and odd, you could also see, as we saw for related acute angle, in terms of acute angle, I could say, this is my triangle, and the reflected triangle here in quadrant 4 will be kind of like this. Any particular point here will be, let's say P as xy. Then its reflected point will be x value same, but y becomes negative. So if this is alpha for us, then that is minus alpha, correct? Because you're going in the clockwise direction. Now, from here also, you can easily show the even odd function. So you can say sine of minus alpha equals to minus sine alpha. Cos of minus alpha equals to cos alpha. And tan of minus alpha is equals to minus tan alpha. Is that clear to you? The cast rule also helps you to get the same result, right? So you could apply the cast rule and see that cosine is positive in quadrant 4, the rest are negative, and that helps you to prove this particular identity, which could also be referred to as a related acute angle. So in that particular case, it is 360 minus alpha, right? So this angle here, which we talked about, is basically, let's say we're saying alpha. So this angle here will be 360 degrees minus alpha. So minus alpha could also be treated as 360 minus alpha. So both are same, right? You could say minus alpha, or you could also say 360 minus alpha. And as we have shown in the previous page, how those identities work. So we have group of identities to work with. We normally refer to them as quotient identity, right? So coming back to Quotient identities are tan theta equals to sine over cos theta. Reciprocal identities are sine is reciprocal of cosecant, cos is reciprocal of secant, tan is reciprocal of cotangent. We had normally say the other way, but both are true. Pythagorean identities is sine square theta plus cos square theta equals to 1. 1 plus tan square theta is secant square theta. 1 plus cotangent square theta is cosecant square theta. Even odd function identities, sine and tangent are odd functions. Cosine is an even function. Co-function identity. Sine 90 minus theta becomes cos theta. Cos 90 minus theta becomes sine theta. Tan 90 minus theta becomes cotangent theta. Related acute angle identities is to see what happens when we see a quadrant. When you are in second quadrant, the angle will be 180 minus alpha. In the third quadrant, 180 plus alpha. In the fourth quadrant, it will be 360 minus alpha. And depending on the cast rule, we could find the identities. So that gives us all the identities. Now, let us look into strategies to prove identities. We have actually seen this strategy while proving the identities itself. Now, here is kind of a statement which summarizes the whole thing. So it says, to prove an identity, this should be an, to prove an identity, one side of an equation is shown exactly equal to the other side of the equation, right? So we are saying that to prove an identity, left hand side should be equal to right hand side. Start from more complicated sides, right? Transform and simplify the expression using algebraic skills and establish identities to get the other expression. So if you start from left side, get the other one. If you start from right side, get the left one. And if you do that, in that case, it's an identity. Otherwise, it is not an identity. Correct? We'll take two examples here. First one is sin x plus cos x whole square is equals to 1 plus 2 sin x cos x. The second one is cot x times secant x is equals to cosecant x. So let's begin with the very first one. So we'll start with the left hand side, which is sin x plus cos x whole square. So if I square this, I get what? I get sin square x plus 2 sin x cos x plus cos square x. Now what is sin square x plus cos square x? Do you remember? Well, that is the Pythagorean identity, right? So sin square x plus cos square x is 1. We're going to use this in this particular identity. Okay. So we know these two terms is 1, so we get 1 plus 2 sin x cos x. Correct? Since we know that this sin square x plus cos square x is 1. That was the Pythagorean identity, correct? So we had shown that sin square x plus cos square x or theta is 1. So that is how we used one of our basic identities to prove identities. So a library of identities help us. So those identities which we just showed were called fundamental identities. Now this is what you get as your right hand side. So you can say that the left hand side is equal to right hand side, and so we have shown that the given equation is an identity. Is that correct? Let's do the last example here, which is cot of x. So we have cot x plus secant x equals to cosecant x. So let's begin again with the left hand side, which is cot of x times, let's use a dot here, secant x. Now cot of x could be written as what? We should write them in sine and cosine. Cot x is cos x over sine x. That is the reciprocal identity for tan. And the secant x can be written as 1 over cos x, right? So what we have used here is a reciprocal identity. So we have used two identities here. This one is a reciprocal identity. Let me write down the names once again here. So we are using reciprocal identity. And this is quotient. So reciprocal and quotient combined. Tan is a quotient identity, which could be written the other way also. Correct? So let's get back to the quotient identity, where we wrote tan theta equals to sine theta over cos theta. We could also write this as cot theta is equals to reciprocal, right? Cos theta over sine theta. Do you get the idea? So in solving identities, the strategy here is to convert to sine and cosine. So one of the strategies which we're talking about is also convert into sine and cosine. So once you do that, what do you find? Well, the cos theta terms cancel away, and what you are left with is 1 over sine x. 1 over sine x is cosecant x, and that is equal to the right hand side. So we have shown that the left hand side is equal to right hand side, and therefore it's an identity. You get the idea. So the idea here is to start from one side, show it equivalent to the other side, use all the algebraic skills and the fundamental identities to prove it. And the strategy which you learn here is it's better to write in terms of sine and cosine. It becomes simpler to simplify and prove. So with that, we'll end this video. But I hope you have fairly good idea about the introduction of trigonometric identities. We have learned many fundamental identities. We have proved them also. I would like you to make a list of these identities, keep them on the side while we continue with proving trigonometric identities in the next lecture. I hope you find it interesting and useful. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.